Welcome to this explainer. I'm absolutely thrilled you're here today because we are about to jump right into a hidden world that you interact with almost every single day, yet you probably never see it. Our goal today is to completely demystify this invisible, highly secure data vault that protects your daily financial transactions. We're going to look at the intense cryptography working behind the scenes of your credit and debit cards.
So think about it for a second. What actually happens in that literal split second after you type your 4-digit PIN into an ATM or when you tap your card at the grocery store? You hear that little beep, and a moment later your transaction is approved. But in those few milliseconds, a massive, highly complex cryptographic conversation is taking place. It's a dense technical reality of banking security, and today we're going to break it all down so you can understand exactly how your money stays safe.
Okay, here's our roadmap for today. First, we'll meet the host security module. Second, master keys in the ZMK. Third, generating everyday security keys. Fourth, creating PINs and CVVs. Fifth, verifying your secure transactions. And finally, number 6, the PIN change process.
All right, Section 1, meet the host security module. Let's dive right into this digital vault that actively protects our financial data.
So right at the very center of the ACI issuer system is the Thales Host Security Module, or you'll hear it called the HSM for short. Now, think of the HSM as an uncrackable digital vault. It's literally a dedicated piece of hardware designed to do one thing flawlessly: perform secure cryptographic operations. It handles the really heavy-duty stuff, like calculating PIN verification values and validating your actual PINs. And to pull this off, it communicates with the rest of the banking network using a standard TCP/IP protocol.
But what makes the HSM a real game changer is how it juggles its workload. It actually operates in 2 totally distinct modes at the exact same time. First up, we've got online mode, which is highly dynamic. When you go buy a coffee, processes like 6 instantly grab an available HSM session from a pool, validate your PIN, and drop the session right back. I mean, it is lightning fast. Then, on the flip side, we have batch mode. This is an allocated, continuous connection used for those long, heavy lifting jobs, like producing thousands of new physical cards at a factory. Because that TCP/IP interface supports multiple sockets, a single HSM can handle your real-time coffee run and massive bulk card creation, literally at the exact same time. Pretty cool, right? Moving on to Section 2, Master Keys and the ZMK. We have our vault, but obviously a vault is totally useless without its combinations. Let's look at how the bank sets up these primary zone master keys. Now, this flowchart perfectly captures how we generate a zone master key, or ZMK. A ZMK is specified at the bank identification number, or BIN, level, meaning a bank might actually have completely different ZMKs for Visa, MasterCard, or Amex. And because security policies are, as you'd guess, incredibly strict, the system never ever handles these keys in the clear. If you look, starting on the left there at Step 1, 3 clear ZMK components are created by customer procedures. They are sent straight into the HSM. The HSM works its magic, encrypts them under its very own local master key, the LMK, and then, down at Steps 6 and 7, it returns the generated ZMK to be safely stored away in the database. All right, Section 3, generating everyday security keys. Let's move down from those massive master combinations to the daily lockboxes, known as everyday working keys. So, modern chip cards, we also call them EMV cards, they require an absolute alphabet soup of specific keys to function. The essentials include the EMV issuer master key, the secure messaging master key, the master key for dynamic CVVs, and the master key for confidentiality. I know, it looks super complex, but the bank basically defines these distinct, highly specialized keys at the BIN level for different networks. It just ensures that absolutely every type of cryptographic message has its very own dedicated lock and key. Okay, so this workflow illustrates how the system creates a card verification key, a CVK. Now, generating this key pair internally isn't a one-and-done deal. It actually requires not one, but 2 separate calls to the HSM, which you can see happening at Steps 2 and 6. The HSM generates the CVK and returns it encrypted under both the local database key, the LMK, so it can be stored internally, and under the zone master key, the ZMK, so it can be securely printed and shared with outside processes. It's doing double duty. Now, what's really interesting here is how this contrasts with generating a key from scratch. This process shows a translation when the bank needs to load an externally generated key. Take a look at step 1. The key arrives already encrypted under the zone master key. The system passes this right to the HSM, which basically acts as a translator. It strips away that ZMK encryption and re-encrypts the key under its own local master key, passing it down to step 6, where it gets stored in the local database. It's honestly like translating a highly sensitive document from French to English in a locked room without anyone outside ever seeing the words.
On to Section 4, creating pins and CVVs. Let's tie these abstract master and working keys back to the daily authentication of the real world. We're going to look at how these exact processes create your actual pins and those 3-digit CVV codes on the back of your physical cards.
So here's where it all connects to your actual daily life. Say you lose your debit card. The bank issues you a totally new card with a new primary account number, a PAN. But you know you really want to keep your old memorized PIN. How in the world do they move it safely? Well, it's a brilliant 3-step sequence. First, the HSM spins up a temporary working key just for this specific job. Second, it translates your existing PIN into a special PAN-independent PIN block. Basically, it unhooks it from your old card number. And finally, it takes that independent block and converts it into a brand new PIN encrypted under the local master key, cleanly tied to your new card number. It is completely seamless for you, but there is some heavy-duty, highly secure lifting going on behind the scenes.
Section 5. Verifying your secure transactions. Next up, we're speeding things up to talk about millisecond security, like the rapid-fire transaction verifications happening while you're standing at the checkout counter.
When you're checking out and you swipe or insert your card, the HSM just explodes into an intense flurry of activity. It has to instantly verify Visa CVVs or MasterCard CVCs using specific network key pairs. And if you punched in a PIN, it's checking that against values in the issuer database. Or if it's a chip card transaction, it's verifying an authorization request cryptogram, an ARQC, using the EMV issuer master key.
And finally, Section 6, the PIN change process. Let's look at the final stage of updating security. What happens when the user decides they want to alter their security and change their PIN?
So here is the legacy process for changing a PIN on an older magnetic stripe card. The ATM sends a PIN change request with your new PIN, but it's encrypted under an ISO issuer working key, or IWK. The authorization router passes this to the issuer processing center. Then the HSM is called upon in step 4 to distranslate that PIN from the ATM's working key right into the bank's local master key. Once it's translated at step 6, boom, the new PIN is permanently stored in the database. It's a very clean, very straightforward translation.
But modern chip cards, they add massive complexity to that exact same task. With a chip card, you aren't just updating a database. You literally have to securely update the physical microchip on the plastic card right there in the ATM. This requires a post-issuance update secured by a message authentication code, a MAC. To pull this off, the HSM uses 3 distinct keys simultaneously. It uses the issuer working key to decrypt the PIN from the ATM, the EMV issuer master key to generate the encrypted response, and the EMV secure messaging master key to generate the MAC, which basically proves the message hasn't been tampered with. It is an absolute symphony of cryptography just to let you pick a new 4-digit number.
Wow, we've covered an incredible amount of ground today in this explainer, from host security modules to zone master keys and dynamic chip card updates. We really took a deep dive into this invisible data vault that protects the modern economy. So my final question to you is this. Next time you swipe, insert, or tap your card at a terminal, will you be able to see the cryptography working behind the scenes? Thank you so much for joining me, and as always, stay curious.